on the cloud, right?
Yes.
Okay,
Yes.
so I am recording right now.
Yeah, it
So
says
we're
it's
on.
recording.
Hmm?
Yes.
It says it's recording. Bhavani, would you like to introduce the speakers, or you want?
No, I'd rather you introduce, but I just want to welcome everyone for the second day.
Okay, right, okay.
So is everyone in now?
Let's wait a couple minutes till 7:30.
Just wait until 7:30. So this is like a half an hour presentation, right? Because after that we have to.
Yeah, half an hour.
Yeah, thank you. So I think now everybody's coming in directly. There's no.
And the numbers will go up, yeah.
Yeah, the numbers will go up slowly, but yeah. I see also Sudarshan is here, which means he's using 2 different accounts.
I don't know how he could do that, but
maybe on 2 machines.
Yeah, right.
Unless he joined after the other short meeting.
No, they're still there.
Okay.
One more minute. Okay, we are set.
Yeah, I guess whenever you're ready.
7:30, yes. Good morning, everyone, or good afternoon, or good evening, wherever you are. And we are now the 3rd day of the conference, 2nd day of the main conference. It's April 22nd, 7:30 Central Daylight Time in the United States. And we welcome you again to IEEE ICD 2020 virtual conference. Today we are going to start the first of our 3 main sponsor presentations, and we are very pleased and to have these sponsors. And I will hand it over to my colleague, the Research Program Committee co-chair, Dr. Dimitrios Gounopoulos, to introduce our very special sponsor speaker. Thank you.
No, thank you very much, Bhavani. My name is Dimitris Gounopoulos, and I'm really very excited to introduce today Dr. Liang Lin, who is a principal engineer in Alibaba. We really would like to extend our thanks to Alibaba, who has been a sponsor to this conference. So without further wait, Dr. Lin, please go ahead and start. I mean, this is going to be a 30-minute talk. At the end, we can ask questions. And after that, I will invite you to continue on to the next talk, which is a keynote talk. Thank you very much, and please go ahead.
Okay, thank you everybody for coming to this talk. So in this talk, I will talk about AnalyticDB, the real-time OLAP database system at Alibaba Cloud. So I will talk about the background, the architecture, and the optimization we have done, and I will conclude with the evaluation results and our future work plan. So Alibaba initially conduct real-time analysis through Oracle, and later on we moved to Oracle RAC. With the rapid development of business, the centralized architecture need to be quickly shift to distributed. So we migrate to Greenplum in 2009 but it has encountered bottlenecks in scalability and concurrency in less than a year due to the rapid growth of the Alibaba business. In order to meet the trend of larger data sets, higher concurrency, higher availability, and more real-time data applications, since 2011, Alibaba database team has firmly embarked on the role of self-development. AnalyticDB, a large-scale real-time analytics database system, was also born at this time. It was the only PB scale real-time analytic database independently developed by Alibaba and supporting many online business such as e-commerce and advertisements inside the Alibaba Group. And in 2014, it's officially available to Alibaba Cloud and to all the public clients. Existing analytic databases are trying to solve similar problems, are trying to get low latencies, data freshness, diversities, low cost, high scalability, high reliabilities. And comparing with all these existing OLAP systems, AnalyticDB carry a much larger scale. We have more than 10,000 physical machines, tens of petabytes of scale of data, and trillions of loads of data. Therefore, when designing and implementing AnalyticDB, it's necessary to not only solve the problems to be solved by the existing OLAP system, and we also have other challenges. For example, the rapid increase in the user analysis needs. The queries has become more complex and more diverse, and how to handle tens of billions of write throughputs per second without affecting the low latency queries. In the complex analysis scenarios, there's a demand for low storage and columnar storage, and also a lot of more complex data types like JSON or vector. And how to design a storage layer that is friendly to all these different storage formats and storage needs. So next, I will introduce the key points of designing and implementing AnalyticDB and explore how AnalyticDB solves these challenges. So this is the architecture of AnalyticDB, and it has the coordinator nodes, which is responsible for receiving requests sent by JDBC or ODBC connections and distributing them to the read nodes or the write nodes down below. The write nodes only handle write requests such as insert, delete, and updates, while the read nodes only handle the read requests. The underlying is our distributed file system, Pangu. It's like HDFS, but it's highly reliable. It's the basic module that AnalyticDB depends on, and many of the storage systems running on Alibaba Cloud depend on the storage system. And the write nodes will flash the data to Pangu for persistence. And on the right side, we have Fushi, which is our resource management and task scheduling system. You can think of like Kubernetes here. Let's jump into the storage system. And the traditional OLAP system processes read and write requests simultaneously on the same link. And if the read and write concurrencies is very large at the same time, the design could result in poor performance due to excess resource competitions. Now, in order to resolve this problem and ensure high performance of the both reading and writing, AnalyticDB adopts a read and write decoupled architecture. Both the read nodes and the write nodes are highly reliable. For the write nodes, when a slave node fails, the master node will evenly distribute the partitions is responsible to other normal slave nodes. And when the master fails, the new master node will be re-elected for replacement. And for the read nodes, user can specify the number of copies of the read nodes. By default, we have 2 copies, and the different copies will be placed on different physical machines to provide high reliability here. And both the read nodes and write nodes are highly scalable. When the write node is added, the master node will be able to automatically adjust the distribution of the partitions to ensure load balancing. And the scalability of the read nodes is also guaranteed by the same mechanism. The coordinator will be able to know how to evenly distribute the read requests across all the read nodes. The AnalyticDB storage revolve around the design goal of Born-for computing. The AnalyticDB storage layer uses the Lambda architecture, and the data on the read nodes include two parts, the baseline data and the incremental data. As shown on the figure, the baseline is all historical data before incremental writings, including index and the detailed data, and the incremental data has no index. Listed on SSD, the AnalyticDB not only support real-time insert, but also support update and delete. When performing delete, AnalyticDB doesn't use the immediate physical deletions, but use the bit set to mark the deleted data loads, as shown on the data here. So copy on write technology is used to support the MVCC, the multi-version control. When the data is deleted or updated, the AnalyticDB will generate a new version of the bit set. The query that is running at this time will continue to use the old versions of the deleted bit set without being blocked by writings. So with this architecture, we'll be able to serve more concurrent queries while have the high write throughputs at the same time because of the locking optimizations. AnalyticDB builds index on all the columns by default, which is quite different from other OLAP systems. We save the index in a separate file, as shown in the figure. And in here, the SQL is a complex query, including structured column conditions and unstructured column condition like JSON or vector. The index engine will first perform an index scan on each conditions to obtain multiple set of line numbers and converting the and all conditions into a union or intersection operation of all these numbers. AnalyticDB has also made a lot of optimizations in the implementation of index engine, such as the K-way merge, index selection CBO, and an index result cache. All of these is try to make the index search or computation much more efficient. And on top of this, we also have a very efficient runtime index selection algorithms. So in the context of massive data analysis, it has following three types of workloads: large-scale dimensional analysis, highly concurrent query, and high write throughputs. Neither low storage nor column storage can meet the above requirements at the same time. AnalyticDB proposes to use a mix of low column structure and set of storage formats, which has the strength of both low and columnar storage, while satisfying the above three types of workloads. For each table, like every k rows of data forms a row group, and in each row group, each column of data is continually stored in a separate block. In the row group is continuously stored on the disk. Because each block has the same data type, it can support very efficient compressions. With this setup, we can support multiple dimensional queries, and we will be able to read the columns much more efficient. And so any column joins, and also be able to support compressed long computing tasks like ETLs. Because the columnar storage queries on extreme wide tables, for example, tables with thousands of rows, the read can be much more efficient. And this format, we can able to support much higher volume of live updates. In our current production systems, we have one instance that have 10 million of TPS coming in, and also have tens of thousands of QPS. or because of this hybrid low column storage. Based on the MPP architecture, AnalyticDB uses pipeline the DAG graph to build an executor that is suitable for low latency and high throughput workloads. AnalyticDB's vectorized execution engine can make full use of the underlying low column storage. Compared with the low base execution engine, the current vectorized engine is more cache friendly and can avoid loading unnecessary data into memory. So we have very efficient code gens, and with this pipeline, we'll be able to also have the corresponding CPU scheduling optimizations so that we can handle mixed workloads for both ETL and short latency queries. We will be able to make sure the short latency queries can return faster while the ETL query is running. And we also have the hybrid execution engine, which is able to determine whether the corresponding operator should be executed in the vectorized mode or executing in the low level. So it can be chosen more efficient depending on the operation is currently be assigned. AnalyticDB combines the CBO cost-based optimizer and RBO rule-based optimizers together to provide a best plan for real-time analysis. Statistical information is the basic information that the optimizer needs to do cost-based query optimizations. And traditional data warehouse only collect limited statistical informations, such as most common value. Commercial database provide users with tools for collecting statistical information, but it's usually depend on experience of DBA, rely on the DBA to decide which statistical data to collect, and depend on the service or the tool providers. We design a query-driven dynamic static information collection mechanisms. The daemon dynamically monitor incoming query workloads characteristics to extract its query pattern. And based on the query pattern, analyze missing or useful informations. On top of this analysis and predictions, asynchronous static information collection tasks are performed in the background. This works aimed to reduce the collection of unnecessary static data while benefiting most of the upcoming queries. With all these static informations, we'll be able to do much more efficient join pushdowns, predicate pushdowns, and join reorders. This is using the APIs we expose at the storage engine. The storage engine is also able to handle all these pushdowns, both the joins and the predicates, and working with the optimizer together to provide a much better execution and plan and better latencies for the users. So coming to experiment. These are three types of queries on real data sets. Full scan, which is scanning the entire table. Point lookups, try to find the lines that match the requirements, and multi-table joins. We test on 1 terabyte and 10 terabytes of data scale, and all three types of queries are completed within seconds. And as you can see from the graph, the query performance of AnalyticDB is slightly impacted by the table size, because we'll be able to fully utilize the columnar storage and also the index we have built. We also have done comparisons with the popular open source products. And we have seen that we have multiple times of performance improvements or speed up compared to all these other open source products. other than these three typical type of queries from the real data set, we also benchmark on TPCH, a very common benchmark framework that's used by many companies and tools. And you can see we also see very significant performance improvements from here. So to summarize, like why it's better. So we talk about pipeline processing from the execution engine. We talk about we build index on all the columns. So different kinds of joins, we will be able to handle all these joins very efficient and hybrid low and column storage. So runtime cost-based index selection, the KV merge of our index data together with the composite predicate pushdowns, and our vectorized engine and the optimized code gen. So all these together, combining both the optimizer compute engines and the storage, we will be able to provide a much better latencies with the current setup. So I would like to talk about our future work plans. And so we launched NLTDB 2.0 in 2016, and about 4 years ago. And this year, we launched NLTDB 3.0. What's different from the current presentation, now we have the separate storage and computation. Both the storage and compute is able to scale on users' demand and depend on users' workload. And also it's a serverless model, and all the compute engines, all the compute nodes can be started on the fly, depending on the query workloads and whether there's a higher ETL query coming in, or user have time patterns. Like for example, they want to run heavy workloads during the midnights, they will be able to do all the serverless schedulings and scale up new workers on demand. And later on, we also have plan for 4.0, and we decide to bring in the transaction support to be a free HTAP engine, supporting both transaction and analytic processing. Cross AC, we want to deploy it across multiple available zones, across different continents to make a global scale. And move to 5.0, we want to have much more better management of the cloud resources. Not only storage and computation, we also plan to separate memories. So workloads can be fully managed. And for example, when the server restarts, when it rebooted, if we already have the memory, if we already have the shared memory, we will not see any performance penalties because all the cache is already there. So we have some initial work on this, and with the 5.0, we'll make the product ready for all the cloud customers. Another hot topic is how we bring machine learning into the system. A lot of people have been talking about autonomous database. So how can this work together to bring a better system? So this is the plans we have for the next 3 years. Okay. Thank you, everyone. Any questions?
Thank you very much. This was a very interesting talk. And in fact, there are some questions. You can look them up at the chat box, but I can actually, I can read them to you, and as I can read them, you can respond. Again, Liang, thank you very much.
I can find that.
Yeah. So the first question is, you mentioned that joins and aggregations are index-based. What happens if a query is received before the index has been built? Can you comment how the indexes are built? This is by Pia Memarja.
Okay. So as I mentioned, we have two sets of data. We have the baseline data. We also have the incremental data. So for all the baseline data, for all the data coming in, like once a while, we will do a fully kind of like compaction, and at this time we build the index. And we also have new data coming in. For those data, we don't have an index. We don't have per field index, but we have kind of min-max for all those data. So when user issue a query to the system for all the baseline data, we will be able to use the index to do efficient retrievals. And for the incremental data, which is stored in memory or SSD, we will do a full scan to, on those data and do the query evaluation on those data, but will not try to extract all the data. As I mentioned, we have some DPNs like min-max, so we'll be able to filter out majority of the data based on this metadata information.
Okay.
So it's a combination of both.
Okay, thanks. Then another question, also if you'd like to, you can also turn on the video so people can look.
Yes, okay, let me see.
Also, I mean, it's up to you. Another question by Murad Uzan is, what's the thing that had the biggest impact on the performance? What's the optimization that kind of improved the performance most?
Okay. Depending on which system you are comparing to, I think the most important part is that we have, it's like database. So we have optimizer and compute engines and the storage all under our control. So we will be able to make the system work very efficient. For example, all the data reading and writing to and from the storage system are in the same format. So we don't need to do any serialization or deserializations. And also all the things are vectorized all the way through the storage to the upper layer, and we can do all the vectorized computations. And also the optimizer, it knows how the data is stored, how the index is stored there. So you'll be able to make the best cost-based optimizations because it knows the system so well. I think that's the most important part when we're comparing with other systems. Like some of the systems, they only have the execution engine and reading data on HDFs per query. Then there's some optimizations, but you will not be able to do this so well. So I think this is one of the important parts. And on top of this, I have also mentioned we are building index on all this data and the vectorized execution.
So it's basically end-to-end optimization, right?
CodeGem, but yeah, right. Basically, I think if you say one point, I think this is the most important part because you own the whole stack. There's a lot of things you can do. And
when you say following the Lambda architecture, so you have a streaming component and a kind of a storage component, do you still have integration over there, or they're kind of?
Oh, sorry, I cannot hear. Can you say that again?
It's okay. I can ask in the end. Let me continue with the questions. Next question is by Walid Aref. He said, do you need supporting graph data analytics, or are you planning to use that?
No, not at this point. Not at this point.
Okay. And next question by Hamid Piraches. What is the latency between propagating update of raw storage to column storage? It's sort of what I was trying to get in. And is columns slightly behind, especially for, and again, for semi-structured data, do you index nested JSON, or?
Yeah.
Do you use, first of all, JSON?
Yes. Okay, so first question about load store and column store. That's one store. So we use the hybrid load and column storage. The data is like for a table, like every k rows from a row group, and within this row group, we use columnar storage. So there's no load store or column store, there's just one store, and we store data in the hybrid low column format. So we'll be able to tune the load group size to be able to be suitable for load-friendly operations. Similarly, we can increase the size of the load groups for columnar-based operations. So the system is able to just address and learn the user patterns. And during the compaction, we'll be able to adjust the size. And for some of the columns, we'll be able to merge them to be able to form one column group. So there's some small optimizations here and there to make it just one store and able to serve the request. We don't have two stores, row and column. So this is the first part of the question. And the second part asks about JSON. Yes, we support JSON and we do index nested JSON as well. It's quite common, like especially for those cloud customers with log data, like many of them are stored in the JSON format. And yes, this is quite popular. This is a very popular use case, and we do support JSON. Yes.
Dimitrios, there was one question we missed, I think. That
Yeah,
was
we missed, I saw it. Yeah, you are right.
Yeah.
Yeah, yeah, so there was a question about the freshness of data. So you update with OLTP and you read it by OLAP. I mean, how quickly this happens?
Will update by OLAP. Okay, so currently this is just an OLAP system. We have, so usually on the upstream, there's a OLTP system. We have, that depends on the tools users using, how they try to sync OLTP data to OLAP. So currently we were able to handle tens of millions of writes coming. And basically the write QPS can be very high because it's highly scalable. As I mentioned, all the write nodes is able to scale, and if it's not sufficient, you'll be able to bring up more write nodes. And so at least for now, we haven't seen any bottleneck of syncing from TP database to this AP database. So this is the current, yeah, this is the current state, yeah.
Thanks. So more questions. Another question is how many concurrent real-time queries can you support, and what are the factors that impact this limit?
Mm-hmm. So that depends on how complex the real-time query is. For those short queries, we can see tens of thousands of QPS, but as the complexity increase, the QPS is able to support by a fixed size of resources start to be limited, right? If you have more joins, or if you have more complex calculations, of course, the QPS will be limited because you only have so many CPU or memory resources. And so this is very hard to say. It depends on the queries. Yeah. So the limiting factors are, I say, from the system side, how many CPUs, memories, or network you have. And from the query side is the complexity of the queries, and how many joins, how many data you are trying to bring in with these queries, and how many calculations you are trying to do here. So yeah, there's a lot of factors. Yeah, it's hard to say. This is also one of the questions asked by our customers. Like, I have like 100 QPS, how many resources I need to buy, and how many compute units I need to purchase.
And of course, it depends
on
the question.
Sorry?
And of course, it depends on the actual queries, right?
Yeah, right. So yeah, so we usually ask them to do some testing. So we also have the service mode. Like if the query is not able to be served by the current setup, and then we will be able to bring up more resources to serve those requests. Yeah.
Thanks. And there are a couple more questions from Hamid Pirahes about column store. I mean, do you index the columns in white tables? And again, the question was if it's slightly later, the commit on the column store, or if it's the same when there is a transaction. And in general, you know, this is the gist here is, you know, is the column store slightly slower or the same as the?
Yeah, okay. Yes, we index all the columns in the white table at the beginning. As we learn more patterns, how users run these queries, we will be able to remove some of the index or try to index less queries during the compaction cycle. As the data is coming in, its initial writing, as I mentioned, it's initial writing in the memory or SSD. And for those data, we don't have full index for this data. We only have the metadata like the min, max, or distinct, or this kind of information layer. And we'll be able to do this, to do initial filterings for those incoming data. And once a while, we would start the compaction cycle. And once the compaction runs and all these data layer will be indexed, or will build index for offline. So it's not like when the data is coming in, we will be updating the index right away. It's, yeah. As I say, it's Lambda architecture. It's there's two flows.
Okay. And another question from Zheng Dong Yan. You mentioned that Analytic DB is able to handle mixed workload. What kinds of workload and what kind of methods you adopt in the workload management manager component?
Okay. It's able to handle mixed workloads, and we handle workloads in two ways. So during the runtime, we have ways to determine slow queries and long queries. Basically, it's similar to the Linux kernel's fail scheduling. For each query, it's sliced into a lot of pieces. And when the pieces runs, we have the counters to increase. As the counter increases more and more, the chance you will get to be scheduled is getting lower. So with this, the slow query, the short running, or we say low latency queries will be able to run faster because it has a chance to get scheduled more often, and the slow queries will slowly being affected. You will be running slower. So this is at the runtime. So this is one way we use to control the CPU cycles to be friendly with the low latency queries. And also we collect the histories for all those queries. So we know ahead of time, like which query patterns run slower or which query patterns runs faster. And for all those queries, we'll be able to do the adjustments accordingly. For example, for some of the ETL queries, we'll be able to run them in a separate worker pool or etc. So yeah, so we have both, like it's kind of real time and plus some of the, we can say HBO, kind of like history-based tunings layer for those mixed workloads.
Thank you very much. Let me just ask one last question. It was a very interesting talk. You mentioned in the end looking at machine learning and how to integrate. What kind of operators are you planning to use, integrate, and when do you planning to do it? When are you planning to do it?
So for the machine learning, currently we are trying to use the machine learning basically more towards how we keep the system healthy, how we do the maintenance and optimizations more efficient. For example, like we have deployed one of the machine learning algorithms in the system so that we'll be able to know which query is running slower, and because we currently have an issue with the optimizer or there's some bug somewhere. So this is, with this information, we'll be able to do adjustments accordingly. So basically try to use the machine learning to make the system run smarter and make user feel more smooth. Like for example, if the current query runs slower, but when you try to run it the next time, we will be able to detect and make some adjustments to that. So this is the current this is one of the area we are currently heavily working on. So yeah, so basically trying to make, let's say, autonomous database, right? So this is one hot topic, and we try to make small steps there. Slowly we'll try to see how far we can get.
Okay. Well, thank you again. Thank you very much. I'm sorry, Bhavani.
So Dimitrios, yeah, I'd just like to add something, that we are very grateful to the Alibaba Group for sponsoring this conference at the goal level. And I hope Alibaba Group will continue to sponsor the ICD events. And also this talk was really great. I mean, I learned a lot in this presentation, and we've quite a few people who have joined in. And also, this will be on the ICDE YouTube page, and so that other people can view it also. And so anything else, any other questions? Otherwise, thanks very much. And thank you so much, yes. And then the general message is that we are going to now move to the webinar room, right? And yes, that starts the keynote address number 3, or which is the keynote address number 1. But today, that's going to start in about, what, 20 minutes?
In 20 minutes.
Yeah, let's give a hand to the Alibaba Group. Thank you.
Thank you.
Thank you.
Bye. Thanks.
Bye.